8 billion tons is the total volume of plastic waste, currently transforming the oceans into a colossal floating graveyard. Why does this global disaster represent a hidden resource mine rather than just an environmental dead end? At first glance, the debris appears to be nothing more than toxic waste, but in reality, the application of hydraulic force and laser precision allows for the conversion of the dirtiest Pacific refuse into a sterile and perfect industrial product. The process is only gaining momentum. This industrial battle for the recovery of the planet initiates in the open sea, an environment defined by high hostility where nature allows no margin for technical error. Over 20 million tons of debris flow into the water systems every single year, with plastic accounting for nearly 80% of that total mass. It only looks obvious that such material would degrade, but in reality, its structural resistance allows it to persist underwater for several centuries. One can notice how it accumulates in massive zones, silently contaminating the entire food chain. To confront this persistent tide, engineers have developed mechanical cleaning vessels that function as industrial predators. The process gets more complex further on. These specialized ships are positioned in critical sectors like the North Pacific Gyre, utilizing two giant hydraulic mechanical arms that extend outward from the hull. The camera glides along these structures as they sweep the surface in a wide fan pattern. Steel nets and conveyors made of stainless steel systematically swallow discarded plastic bottles and abandoned fishing nets. A single operation of this scale continues for 8 to 10 hours without interruption. One can notice the slow tilt of the boom as it lifts up to 10 tons of marine waste in a single cycle. But this is just the beginning of the extraction phase. Why is the strategy shifted when moving from the deep ocean to inland waterways? Rivers and canals often contain dense barriers of waste that block the flow of water before it ever reaches the sea. Here, heavy excavators mounted on large dump trucks take over the primary workload. These machines utilize steel clamshell buckets that possess an individual weight of nearly 1,000 pounds. The equipment gradually lowers these buckets to tear through the surface, extracting heavy mixtures of bags, organic branches, and discarded tires. Every individual lift removes exactly 1,000 pounds of debris from the water. With the constant application of hydraulic power, a single technical team can clear a river segment measuring several hundred feet in length in only a few hours. It is visible how the mechanical claws move with 10 times the speed of any manual labor effort. The roar of the engines signifies the transition to the next level of processing as the raw material is prepared for transport. The movement of the heavy components remains steady and calculated as the waste is loaded for its final transformation. 5 tons of unwanted material are accumulated by a single specialized vessel during a standard 8-hour shift. Why must these compact boats operate on such a strict schedule despite the vast scale of the ocean? It only looks obvious that the waste should be removed as quickly as possible. But in reality, the logistics of the return journey to solid ground require precise coordination to prevent the harbor from becoming congested. Specialized vessels, engineered exclusively for the transport of this specific cargo, carry the debris toward the coastline with steady mechanical persistence. This signals the transition toward order within the center of the environmental chaos. The process is only gaining momentum. One can notice how hydraulic conveyors begin the discharge of the massive waste mountain into the factory reception zone as soon as the vessels dock at the harbor. The equipment gradually moves the saturated pile, which appears as a confused and soiled mass, where various polymers are intertwined with heavy metals, saturated wood, marine vegetation, and thick organic sludge. At first glance, the pile is total chaos, but the technical objective at this stage is to isolate valuable components from hazardous substances. Workers conduct an immediate visual inspection of the intake, manually extracting oversized objects that possess the potential to catastrophically damage the downstream machinery. This includes the removal of heavy steel netting and discarded tires. Transition to the next level. The remaining material is pushed by mechanical loaders into an industrial sorting system. 1,000 millimeters or more is the diameter of the trommel drum, a massive rotating cylinder that functions as a high-capacity mechanical sieve at the heart of this stage. It is visible how the cylinder rotates ruidosement while classifying the incoming waste stream strictly by physical dimensions. Fine sand, calcium shells, and small fragments of debris fall through the calibrated perforations of the drum. Meanwhile, Larger bottles and packaging containers continue their movement through the interior of the apparatus. But this is just the beginning. The residual flow, now consisting primarily of plastics and nylon fibers, is transferred onto a manual sorting conveyor belt. Human vision remains a technical necessity at this junction to identify and separate individual material categories, establishing the foundation for the upcoming critical phase. It seems simple to distinguish materials, but in reality, this step ensures that the plastic is isolated from glass and metal contaminants with absolute precision. The plastic, which is being converted from a discarded pollutant into a vital industrial resource, is moved forward for specialized processing. Everything only gets more complicated. The separated plastic now presents a challenge in the form of microscopic contamination. These fragments have spent months or even years submerged in the marine environment, becoming coated in thick layers of salt, industrial oil, and active bacteria. Successful recycling requires that the material become surgically clean before any further thermal or chemical transformation can occur. The equipment gradually feeds the plastic into mechanical washing tanks, where high-speed rotating shafts generate a violent and turbulent flow. One can notice the debris splitting with a crack under the hydraulic pressure of the water. The material is ready to move to the next processing phase without haste. 160 to 180 degrees Fahrenheit is the intense thermal range reached within the advanced cleaning installations. Why is such extreme heat necessary for what appears to be a simple washing process? While a standard rinse might remove surface dust, only this precise temperature window, when synchronized with specialized chemical cleaning agents, can successfully dissolve stubborn salt deposits and oils to neutralize every potential contaminant. The plastic material remains trapped in this chemical and thermal bombardment for a duration of 15 to 30 minutes. But this is just the beginning. One can notice how the material transitions from the heat bath into a high-speed drum scrubber. It is visible how the equipment rotates with immense centrifugal force while firing high-pressure water jets to desalloge every remaining grain of abrasive sand. At first glance, the mechanical scrubbing looks like the final step, but in reality, the most critical separation task follows immediately. How can the system distinguish between different types of polymers that are now inextricably mixed together? The answer lies in simple physics and the fundamental laws of buoyancy. Within a massive flotation tank, the specific density of each fragment determines its ultimate destination. Polyethylene terephthalate, commonly known as PET, and used for liquid containers, immediately sinks to the bottom of the tank. Simultaneously, lighter plastic variants remain on the surface, allowing the equipment to achieve a perfect separation without a single instance of human intervention. The process is only gaining momentum. Automated conveyors transport the purified material into a drying chamber, where hot air at 170 degrees Fahrenheit circulates continuously. This stage does not end with moisture removal alone. Advanced ozone systems are integrated into the airflow to oxidize and eliminate any lingering organic odors that may have survived the initial wash. The camera glides along the discharge chutes, where the scent of stagnant water or salt spray has been completely eradicated. Only pure plastic remains, prepared to be destroyed so it may eventually be reborn. Everything only gets more complicated. Action now shifts to one of the most violent and technically precise moments of the entire industrial operation. The clean bottles, once recognizable in their original form, must now be reduced to a perfectly uniform state. Huge blades rotate at high velocities to prepare for the mechanical shredding phase. From here, the transformation moves to the next phase of processing. 2,000 to 3,000 pounds of plastic are consumed every hour by high-speed granulators that operate with mechanical ruthlessness. Inside the armored chamber, hundreds of specialized alloy blades rotate at several thousand revolutions per minute. Why is this violent reduction of material necessary? To the casual observer, the process seems like mere destruction, but in reality, it is a calculated transformation of bulky bottles into tiny fragments known as flakes. This surface area expansion ensures that the material will melt significantly faster in subsequent stages, which reduces energy consumption by up to 40%. The process is only gaining momentum. One can notice how the equipment gradually turns a mountain of containers into a constant stream of plastic confetti within a few minutes. At first glance, the shredding appears to be the final step of preparation, but even after intensive washing, microscopic intruders may still persist in the mix. A single fragment of wood or a piece of plastic with an incorrect color profile is enough to compromise the integrity of the entire batch. Transition to the next level. High-speed lasers and optical sensors examine every individual flake with millisecond-level precision. If the computer identifies an impurity, such as a microscopic metal shard or a foreign polymer, it triggers a blast of compressed air with the accuracy of a marksman. This focused air jet removes only the defective particle from the main flow without disturbing the surrounding flakes. Everything only gets more complicated as a single sorting unit processes more than 1,000 particles every second. It is visible how the machinery maintains a precision rate exceeding 95%, establishing absolute order over the chaotic mixture. The purified material moves toward the transformation phase. Approved flakes enter a massive extrusion unit where the temperature rises to 520 degrees Fahrenheit. In this extreme heat, the solid plastic liquefies into a viscous and shimmering molten mass. A giant rotating screw pushes this liquid forward through a series of ultra-fine metal screens that capture any remaining contamination that managed to bypass the optical lasers. The process is only gaining momentum as the plastic is forced through the die. Millions of small granules called pellets are formed when the purified plastic is cut underwater. These granules serve as the essential raw material for the next generation of products. But even at this stage, the familiar shape of a bottle has not yet emerged. Pellets are reheated to 480 degrees Fahrenheit and injected under high pressure into precision-machined steel molds. This does not immediately create a full-size container, but rather a preform. The camera glides along the production line, where these thick-walled tubes, resembling glass test tubes, begin to take their final structural form. The molten stream goes further along the production chain. Millions of future containers occupy a minimal volume thanks to this compact engineering design. Why is such a condensed form utilized before the final manufacturing stage? This structural density allows for the efficient transport of vast quantities of material to their final destination, where they will undergo the transformation into finished bottles. These preforms are manufactured with a robustness specifically calculated to withstand the stresses of the final metamorphosis. The small preforms are subjected to intense heat once again until the material reaches a state of softness and flexibility. One can notice the plastic gaining the consistency of heated rubber as the temperature rises. The machinery directs the softened tubes into the blowing mold, where high-pressure compressed air is injected with sudden force. It is visible how the physics of expansion take over as the plastic stretches instantly to 4 or 5 times its initial dimensions. The material presses firmly against the cold interior surfaces of the metal mold. But this is just the beginning. In a span of mere seconds, the small tube evolves into a structurally perfect bottle. Modern production lines discharge thousands of these units in rapid succession with a rejection rate that remains near zero. Everything only gets more complicated as the speed increases. The equipment gradually moves the newly formed bottles through a rapid cooling chamber to lock the molecular structure while the plastic is still vulnerable to deformation. This is followed by a rigorous diagnostic phase. Lasers and high-resolution optical sensors scan every millimeter of the surface to detect microcracks or air bubbles. The system monitors the thickness of the walls to ensure structural integrity across the entire batch. Additional chemical analysis is performed on containers intended for beverages to confirm the total absence of harmful residues. At first glance, the inspection seems routine, but in reality, it represents a level of military-grade scrutiny that prevents defective units from reaching the consumer. The process is only gaining momentum. Automated robotic systems arrange the thousands of validated units onto pallets with millimeter precision for logistics. One can notice the synchronized movement of the mechanical arms as they stack the shimmering, sterile containers. 8 billion tons of waste once threatened the stability of the marine ecosystems at the start of this industrial cycle. The transition to the next level shows how what was once toxic debris in the Pacific Gyre has been purified through the application of heat, water, and laser light. It only looks obvious to see these bottles as simple objects, but in reality, they represent the successful closure of a circular engineering loop. Engineering and industrial determination allow for the conversion of environmental errors into sustainable resources. The factory functions as a mechanism for transformation where nothing is lost and every gram of material is repurposed. The ocean environment undergoes a gradual recovery as these processes replace the need for virgin plastic production. Thus, the material completes its journey through the modern industrial chain, returning to the economy as a valuable asset. This concludes the primary stage of the reclamation process. $3.5 trillion represents the immense economic scale of California. This industrial and agricultural powerhouse now encounters a silent and lethal adversary in the form of the most severe drought recorded in the last 1,200 years. As riverbeds dry into cracked earth and mountain snowpacks vanish, engineering presents a solution once deemed impossible by converting the saltwater of the Pacific Ocean into a potable resource. Why are colossal machines being constructed along the coastline at such a massive scale? The answer lies in the intense heat radiating from the parched soil of the Central Valley. The state functions as the primary agricultural engine for the United States, providing 1/3 of all vegetables and 2/3 of the nation's fruits and nuts. This green miracle, sustained in a semi-arid environment, demands 80% of all water consumed within the state borders. Historically, the region relied upon the Sierra Nevada, a massive mountain range that acted as a natural reservoir by accumulating snow during winter months. It only looks obvious that the snow would melt and provide fresh water during the summer, but in reality, this natural cycle has completely collapsed. Snow levels have diminished drastically, forcing vital reservoirs such as Shasta and Oroville down to critical levels of 40% capacity. Fertile soil has begun to fracture, disintegrating into clouds of red dust that drift across the landscape. One can notice how the landscape transforms into a barren wasteland as the moisture evaporates. But this is just the beginning. The Pacific Ocean now serves as the only viable source for survival. Moving the ocean inland requires an architectural network of industrial arteries consisting of massive pipelines made from carbon steel and high-density polyethylene. Engineers have designed these conduits with diameters ranging from 2 to 3 meters, creating spaces wide enough for a vehicle to pass through. These structures act as underwater fortresses designed to withstand the relentless corrosion of salt and the crushing pressure of the depths. Installation of these segments follows a rigorous mechanical protocol. Heavy cranes lower sections of pipe measuring dozens of meters in length toward the seabed with calculated precision. Divers and specialized machinery work in tandem to secure every joint using high-pressure connectors and hermetically sealed welds. One can notice the slow, deliberate movement of the crane booms as they fight the resistance of the waves. It gets more complex further on. A single pipeline with a diameter of 63 centimeters can extract 15 million liters of water every 24 hours. This translates to a flow rate of over 10,000 liters per minute, a continuous torrent propelled by industrial pumps that overcome gravity to transport the sea toward the shore. To ensure stability, the pipes are anchored into the ocean floor with steel frames and deep-driven piles to prevent displacement by powerful underwater currents. At first glance, the intake process appears to be a simple mechanical suction, but in reality, the raw water entering the system carries the entire complexity of a marine ecosystem. The equipment gradually pulls in the brine, where the process of transformation into fresh water is only gaining momentum. The raw intake remains the first step in a chain of extreme pressure and filtration. The water moves steadily through the steel throats of the intake system toward the treatment facility. Each liter represents a calculated effort to counteract the drying of the continent. From here, the transformation moves to the next phase of processing. 4.5 millimeters is the maximum diameter allowed for any solid particle to penetrate the initial intake barriers of the desalination plant. Why is such a strict threshold necessary when dealing with trillions of liters of ocean water? Without this mechanical gatekeeping, the high-precision pumps located further down the line would be obliterated by biological and mineral debris in less than 60 seconds. The raw intake is essentially a chaotic soup teeming with algae, sand, jellyfish, crabs, and small fish that must be filtered out before the chemical transformation can even begin. One can notice how massive screens and heavy-duty steel grates act as relentless sentinels hundreds of meters from the shoreline at the mouths of the intake pipes. This is the first line of defense, a brutal war of barriers designed to safeguard the delicate machinery from the unpredictable nature of the sea. It gets more complex further on. It only looks obvious that this screening makes the water safe, But in reality, an invisible army of sediments remains suspended in the flow. Fine sand, silt, and microscopic particles create a turbid liquid that would shred the sensitive membranes of the core system. To neutralize this threat, the plant utilizes one of the most reliable forces in physics, which is gravity. The water is channeled into colossal filtration basins where thick layers of sand serve as a natural sieve. The liquid descends slowly through the microscopic voids between the mineral grains while the impurities become trapped in the upper strata. One can notice how the equipment gradually removes, washes, and recirculates the dirty sand in a continuous and rhythmic cycle. But this is just the beginning. Why are chemical additives necessary after the water has already passed through layers of sand? Certain particles are so small, they effectively bypass the sand filter, measuring less than 1/10 the thickness of a human hair. To capture these microscopic ghosts, engineering turns to the science of flocculation. Giant mechanical paddles rotate ceaselessly in deep tanks, while automated injectors introduce coagulants like ferric chloride into the stream. The camera glides along the surface where the chemical reaction begins to take hold like a magnetic force. The coagulant binds the fine dust and invisible debris together, forcing them to coalesce into larger, heavier flakes known as flocks. Suddenly, the microscopic waste gains mass and sinks to the bottom of the basin as a heavy sludge, leaving a significantly clearer layer of water above. Everything only gets more complicated as the process targets the most resilient opponent. The life, the sand, and the silt have been extracted, but the primary enemy remains dissolved in the liquid, invisible and lethal to both agriculture and humans, which is the salt. One can notice how the water appears pristine, yet it still contains 3.5% salt by volume. To remove it, the facility must generate a physical force capable of challenging the molecular bond of the water itself. Before reaching the final stage, the water must pass through a last guard of honor, known as the cartridge filters. These are dense, pressurized cylinders of compressed fibers designed to trap any remaining particles between 1 and 5 microns in size. This obsession with absolute purity ensures that no solid matter ever touches the most expensive technology in the facility, the reverse osmosis membranes. The process is only gaining momentum. Reverse osmosis is the precise point where raw industrial engineering meets the complexities of molecular physics. Salt and water share a powerful chemical affinity, as sodium and chlorine ions cling to water molecules with extreme tenacity. The water is now prepared to enter the high-pressure chambers where this bond will be systematically broken. The liquid stream moves toward the final transformation stage, where the salt will eventually be separated from the life-giving water. 60 bar is the exact level of pressure required to break the molecular bond between salt and water. Why is such immense force necessary to separate these two elements? At first glance, the mixture appears inseparable because the salt is dissolved at a fundamental level. But in reality, the desalination process requires overcoming the natural osmotic pressure that keeps the brine stable. High-power centrifugal pumps begin to rotate with a deep hum that causes the surrounding concrete floor to vibrate. The process is only gaining momentum. The equipment pushes the liquid against semi-permeable membranes with an overwhelming force of 60 bar. This value is 60 times the pressure that the Earth's atmosphere exerts on a human body at sea level. One can notice how the hydraulic systems maintain this tension without a single millisecond of fluctuation. This intensity is equivalent to the weight of a full-grown elephant resting entirely upon a human thumb. Under this crushing weight, the water molecules have no choice but to move forward. They are forced through the membrane layers, where pores are so microscopic that only pure molecules of hydrogen and oxygen can navigate the openings. The salt particles, being larger in size and carrying an electrical charge, are barred from entry and subsequently repelled. It is visible how the molecular sieve functions as a physical barrier. A concentrated brine solution exits from one side of the system, while on the other, droplets of fresh water emerge, liberated by force from their saline companion. But this is just the beginning. For the rigorous standards of California, this level of filtration is considered insufficient for the final product. The liquid enters a second stage of reverse osmosis, where the equipment gradually subjects the water to even more restrictive membranes. These tighter barriers are designed to remove stubborn trace elements like boron and any remaining ions that bypass the initial phase. One can notice how the sensors monitor the conductivity of the stream to ensure total mineral removal. The result is a liquid that is no longer merely water, but a substance characterized by absolute technical purity. The camera glides along the stainless steel piping as the processed fluid moves toward the final stabilization tanks. Everything only gets more complicated as the chemistry must be balanced before the water can be distributed. The minerals are gone, leaving behind a blank canvas of hydration ready for the next industrial step. The pure stream flows steadily into the collection reservoir, completing this stage of the transformation. Zero impurities are the result of the desalination process that transforms the chaotic chemical composition of the ocean into a controlled liquid order. Why do we move millions of liters of fresh water across such vast distances? It would seem logical to use the water directly at the shore, but the farms and expanding urban centers are located hundreds of kilometers away in the interior of the continent, shielded by high mountain ranges. The primary challenge ceases to be chemical and becomes purely geographic. Moving an entire river requires a massive technical intervention. 700 kilometers is the approximate length of one of the greatest infrastructure feats in human history, known as the California State Water Project. This artificial river of concrete, the California Aqueduct, cuts through the desert landscape like a long blue scar to transport water from northern mountains to the arid southern regions. The desalinated seawater is integrated into this existing vascular network, but the geography presents a titanic obstacle in the form of the Tehachapi Mountains. At first glance, moving water across a mountain range seems impossible, but in reality, gravity is overcome by sheer mechanical force. The Edmondstone pumping station was engineered as the most powerful facility of its kind in the entire world. Inside the station, one can notice giant electric motors, each approximately the size of a two-story house, which function to push thousands of tons of liquid uphill. These machines elevate the water column to a vertical height of 600 meters in a single continuous impulse. It is the physical equivalent of pumping the volume of an entire river to the roof of a 150-story skyscraper. Energy consumption reaches staggering levels, requiring an expenditure of billions of dollars. But this is just the beginning. The water, now a hybrid mixture of processed ocean water and melted mountain snow, begins to flow by gravity toward the Central Valley. This transition turns the desert into productive almond orchards and lettuce fields that provide food for the entire nation. Yet the cost of transporting seawater over mountains remains high. Everything only gets more complicated when considering if a closer water source exists directly beneath the city streets. California has determined that in the conflict against drought, there is no such thing as waste, only resources that are not yet fully utilized. One can notice the transition into the world of wastewater recycling, where sewage is purified into drinking water. It looks superficially simple to discard wastewater, but in reality, this represents the final frontier of technical efficiency. The process begins in the dark urban sewer systems, where every sink, drain, and industrial pipe feeds into toxic underground streams. When this mass reaches the treatment plant, it consists of a complex mixture of debris, paper, plastic, branches, and sand. The initial stage of purification is mechanically brutal. Grades made of stainless steel intercept solid waste, functioning like massive teeth that filter the flow to remove rags and discarded plastics. The equipment gradually directs the liquid into primary sedimentation tanks, where the laws of physics are utilized to separate the components. As the water velocity decreases, the heavy sludge consisting of organic matter and paper fibers begins to sink slowly toward the bottom. The sludge settles in a thick layer at the base of the tank. The material is ready to move to the next processing phase without haste. Billions of microorganisms awaken as oxygen is injected furiosamente into the aeration tanks, creating a biological jacuzzi that facilitates the next stage of purification. Why invoke nature in the middle of a high-tech industrial facility? It would seem that advanced machinery alone could handle the waste, but these invisible workers digest organic matter and dirt that no mechanical filter could ever capture. The solid waste has been removed, yet the water remains dark and saturated with dissolved substances that require a biological offensive. One can notice how the water churns under the pressure of the air, feeding the bacteria as they perform their critical task. But this is just the beginning. The process moves to a higher level of precision. After the bacteria finish their work, The liquid is forced through microfiltration and a second round of reverse osmosis. At first glance, this technology appears redundant, but in reality, it serves as the final barrier of absolute safety for the entire system. These white tubes house specialized membranes that block viruses, bacteria, hormones, and pharmaceutical residues with total efficiency. Nothing passes through these microscopic pores except the individual water molecule itself. The liquid emerging from the pipes possesses a distinct brilliance, and it is officially designated as neophyte water. Everything only gets more complicated as the purity levels exceed standard expectations. Is it possible for water to be too clean for human use? 100% purity creates a technical paradox that engineers must manage immediately. The water exiting the reverse osmosis membranes is so devoid of minerals that it becomes chemically aggressive. If this liquid were pumped directly into the municipal grid, it would begin to dissolve the metal of the distribution pipes, rapidly corroding the city infrastructure. Furthermore, perfectly pure water lacks any discernible taste, as the flavor humans associate with high-quality water comes from mineral impurities. Technicians must now intentionally reintroduce substances into the stream in a process known as controlled remineralization. Huge tanks serve as the site where calcium and magnesium are dosed back into the water with pharmaceutical precision. It is visible how the chemical balance is restored, adjusting the hydrogen potential to ensure the water is neutral and safe for both human consumption and the steel veins of the city. Transition to the next level. The water has achieved a state of chemical perfection and is ready for the final distribution phase. Giant pumps drive this reborn water into massive storage reservoirs before injecting it into the municipal network. While this industrial water can cost 2 to 4 times more than traditional sources, it functions as a critical insurance policy against climate instability. Natural reservoirs depend entirely on the unpredictability of rainfall, whereas this factory relies strictly on energy and mechanical engineering. It represents a source that never runs dry, regardless of the weather. The process is only gaining momentum. One can observe how the lush green fields of the Central Valley continue to flourish, defying the surrounding desert conditions. Think of the immense physical journey this liquid has completed to reach this state. This water was once a salty wave crashing on the coast, or raw sewage flowing through underground tunnels. It was crushed by 60 bars of pressure, forced through membranes, pumped over mountain ranges, and entirely reconstructed at a molecular level. California has demonstrated that when natural cycles fail, human ingenuity assumes full command of the resource. In the 21st century, water has transitioned from a gift of the atmosphere into a refined product of heavy industry. We have successfully closed the loop, constructing a self-sustaining water cycle that depends on energy and steel rather than clouds. The material leaves the facility, transitioning into a calm stage as it enters the homes of millions. Thus, the steel and machinery ensure that the region will not suffer from thirst. This concludes one of the key stages of industrial water production. 625 meters is the height at which the road surface of the Huajing Bridge floats above the canyon floor. Why construct a crossing at an altitude nearly twice that of the Eiffel Tower? One can notice how vehicles do not merely span a river, but literally pierce through layers of cloud cover in a landscape of dizzying proportions. This structure, which opened in September of 2025, represents a global record in bridge engineering. At first glance, the altitude alone is the primary marvel, but the technical ambition extends even further. Engineers integrated a glass-walled cafe directly into the crown of one of the support towers, suspended over the abyss. This project marks a definitive boundary in modern construction, where theoretical impossibility is transformed into reinforced concrete. To grasp the necessity of such gravity-defying architecture, the focus must shift downward to the geographical conditions of Guizhou province in western China. It is visible how the terrain resembles earth crushed by immense force. Over 92% of this territory is comprised of jagged mountain peaks and unforgiving plateaus. 8 major river systems carve through the crust, creating valleys of such extreme depth they isolated millions of inhabitants for centuries. Transportation in this environment is a relentless physical struggle against the natural topography. The technical objective was the creation of the Liuji-Anlong Expressway. This vital artery serves to integrate isolated communities into the national infrastructure. However, the path was obstructed by the Huajing Canyon, a massive rift bisecting the landscape via the Beipan River. Engineers encountered a binary dilemma where both potential solutions carried significant structural risks. Everything only gets more complicated when considering the first alternative. Constructing the route along a smoother trajectory would require placing the bridge near the mountain summits. At those elevations, wind speeds reach lethal velocities capable of destabilizing standard structures. The second option involved lowering the bridge height to a more conventional level. While seemingly safer, this path would force the highway across unstable slopes and through excessively long tunnels, significantly increasing the probability of catastrophic landslides. Therefore, the decision was made to elevate the structure into the atmospheric zone at 2,050 feet. This height of 625 meters presented only the first half of the engineering challenge. The canyon forms a massive V-shape, resulting in a free span exceeding 1,400 meters between the opposing cliffs. At this monstrous scale, conventional engineering principles cease to be effective. The world's tallest rigid beam bridge would succumb to structural failure under its own massive weight at such lengths. An arch bridge, even of record-breaking dimensions, could not physically reach the distant cliffside. Even the most robust cable-stayed designs lacked the mechanical strength required to bridge such a vast atmospheric void. Only one viable technical solution remained for the team. The process is only gaining momentum as the design shifts to an ultra-long span suspension system. This configuration functions as a continuous ribbon of steel and high-strength concrete suspended in the sky. The fundamental theory involves the vertical erection of two massive towers to support the primary weight. From these points, two main cables are draped to provide the tension necessary to hold the roadway in place. The transition to the next level of construction begins as the foundations take hold in the rock. 828 meters, exactly the height of the tallest building in the world, represents the scale of the structure being anchored into a terrain that actively rejects human presence. Why must such immense vertical power be balanced by hidden subterranean strength? At first glance, the task appears to be a matter of simple construction, but in reality, the foundations must prevent the entire bridge from being physically torn away from the earth by the forces of nature. The geological composition of the site presented the first lethal challenge to the project. The soil here lacks solidity. One can notice how the ground consists of weathered rock, riddled with invisible fractures and treacherous groundwater that flows through hidden veins. A single error in calculation during this phase would result in the tower sliding into the abyss. The technical response from the engineering team was a combination of brute force and surgical precision. They drove 24 massive concrete piles deep into the belly of the earth, each reinforced with specialized steel designed to withstand seismic tremors. It gets more complex further on. The equipment gradually secures the site as the piles are set. They did not simply build upon the rock, they effectively stitched the tower into the mountain itself using these deep-reaching vertical anchors. However, a suspension bridge ultimately lives and dies by its anchors. It is visible how these components function like muscles holding a rope in a titanic tug-of-war. These anchors must endure the constant tension of thousands of tons, pulling relentlessly toward the center of the valley. On the Zhengfeng side, the solution was found in pure mass. Engineers constructed a gravity anchor, which is a colossal concrete block with a total volume of 164,000 cubic meters. This is not the limit of the scale. To provide a technical perspective on this volume, it represents enough concrete to fill dozens of Olympic-sized swimming pools. The camera glides along the massive structure where every ton is compacted into a single immovable cube embedded into the mountain slope. But this is just the beginning. On the opposite side, in Guanling, the natural environment dictated a completely different strategy. A steep mountain rose directly behind the tower, leaving almost no flat ground available to accommodate a giant concrete block. Space was non-existent. If the engineers could not build upon the mountain, they would be forced to build inside of it. The process is only gaining momentum as they transition to the next level of structural integration. The engineers opted for a specialized tunnel anchor to secure the tension cables within the solid rock. The material is prepared for the next phase of integration into the mountain. 9,000 tons is the weight of just one of the two primary cables that this mountain infrastructure must support. Why fix the anchoring cables directly into the rocky skeleton of the massif instead of building external concrete blocks? At first glance, the geology of the canyon represents an obstacle, but in reality, engineers transformed it into a structural ally. By transferring the immense tension of the steel lines directly into the planetary mass, they maximize stability while significantly reducing the physical footprint of the construction site. The rise of the colossal towers began immediately after the foundations were locked into the stone. One can notice how the two main pillars ascended toward the clouds in successive vertical increments, reaching final heights of 262 meters and 205 meters respectively. Why are these heights reached under such extreme conditions? These are not urban skyscrapers shielded by surrounding buildings, but structures perched on the jagged edge of a precipice. The equipment gradually lifts materials while winds oovum through the narrow canyon corridor, testing the spine of the system every hour. The towers serve as the backbone, engineered with high-strength steel to endure the passage of heavy freight trucks and the sudden impact of seismic activity. It only looks obvious that the pillars stand still, but in reality, they must remain immobile while absorbing violent vibrations that would collapse standard structures. The process is only gaining momentum. Imagine holding a thin steel ribbon steady while a powerful earthquake attempts to shake your grip. That is the daily mechanical reality for these pillars. Everything only gets more complicated as the vacuum between the towers remains to be conquered. A temporary catwalk was installed hundreds of meters above the river surface, creating a narrow workspace where specialists would eventually weave the main cables. But a fundamental problem emerged regarding how to bridge the initial 1,400-meter abyss. One can notice the difficulty of the environment, where helicopters cannot fly safely due to unpredictable gusts, and the river below is too distant to be of tactical use. High-power drones were deployed to carry the initial pilot line across the void. The camera glides along the trajectory of these machines as they guide the wire with a level of precision that human hands could never achieve in high-altitude winds. With the pilot line secured, the temporary walkway took its physical form. Everything was finally prepared for the most critical phase involving the assembly of the primary lifelines. These main cables are not singular units, but complex bundles consisting of tens of thousands of individual steel wires. It is visible how the operation requires manic precision from the workers positioned on the suspended catwalk. Each individual strand is comprised of 91 high-strength steel wires, with each wire measuring only 5.7 millimeters in diameter. Workers pulled these metallic threads back and forth between the anchors, located at points 200 and 500. The metal lays in dense layers as the cables gradually gain their full structural thickness. The spinning process continues until the massive bundles reach the density required to sustain the bridge for decades. Transition to the next level. This stage of the assembly ensures that the core of the suspension system is perfectly balanced before the deck segments are introduced. The cable weaving concludes this phase, opening the road to the final formation of the crossing. 2 millimeters is the maximum allowable positioning deviation for each individual cable segment. Why is such surgical precision necessary in a structure spanning 1,500 meters? While high-altitude winds exert constant pressure, any greater error would compromise the structural integrity of the entire suspension system. Global Positioning System technology supervised the installation of every wire, ensuring that the engineering matched the theoretical design with absolute accuracy. Once every wire reached its designated position, a specialized compaction machine began its transit along the bundle, squeezing the strands into a dense, geometrically perfect cylinder. The process is only gaining momentum. This steel core was subsequently encased in multiple protective layers designed to withstand corrosion and the relentless passage of time. It is visible how the equipment seals these 9,000-ton steel arteries, preparing them to support the massive weight of the crossing. Only after the completion of these primary supports could the structure begin to take the recognizable form of a bridge. Everything only gets more complicated as the moment of truth arrives. Suspender cables, acting as vertical steel claws, were lowered and secured to the main spans to prepare for the lifting of the road deck. The road surface where vehicles will travel was not constructed in situ, but rather assembled like a massive aerial puzzle. 93 separate steel segments, each weighing several hundred tons, were hoisted individually from the floor of the valley. One can notice the tension in the lifting cables as a crane pulls a colossal weight to a height of over 600 meters. At first glance, the lift looks steady, but in reality, gravity and wind forces constantly threaten to rotate or tilt the heavy sections. Engineers performed continuous tension adjustments to prevent any twisting of the emerging platform. This slow and dangerous industrial ballet required total synchronization between the ground crews and the winch operators. But this is just the beginning of the technical achievements. 439,000 cubic meters of concrete were required for the Huajiang Bridge. To visualize the scale of this volume, one would need to imagine 176 Olympic-sized swimming pools filled to the brim with liquid stone. It gets more complex further on. Engineers utilize the waste rock excavated from the mountains, effectively turning industrial debris into a high-performance green mineral powder. They substituted 20% of the traditional cement in every cubic meter with this processed powder. Such a decision transformed waste into structural strength while simultaneously reducing the environmental footprint and the total cost of the materials. The equipment gradually moves away as the cured concrete and gleaming steel reach completion. But will the structure withstand the actual operational stresses? There was no room for theoretical doubt in the final phase. During August of 2025, the engineering team initiated the definitive load test using brute physical force. 96 heavy trucks, loaded to their maximum capacity, rolled onto the bridge deck in a synchronized formation. 3,700 tons of total weight began crushing down on the asphalt and the underlying steel. It is visible how the tires press into the surface, while the roar of nearly 100 engines vibrates through the metal. More than 400 sensors distributed across the entire structure monitored every physical response in real time. These instruments recorded cable tension, vibration frequencies, and structural deformation with millisecond accuracy. The bridge remained firm, proving that the calculated tolerances were correct and that the structure was ready for service. This concludes the primary testing phase, opening the road to final certification. 625 meters above the canyon floor, absolute safety depends entirely on the mathematical precision calculated years before construction began. Why did the engineering team face such brutal physical challenges during the assembly of this structure? The Huajiang Canyon functions as a massive natural wind tunnel where atmospheric pressure creates extreme conditions. Air gusts frequently accelerate to level 14 on the Beaufort scale, which is equivalent to the devastating force of a hurricane. The work stopped whenever the wind velocity exceeded level 6 to prevent the mechanical displacement of workers into the abyss. One can notice how the human teams began their shifts at 6 in the morning and continued until total darkness consumed the gorge. The workers moved with slow, deliberate steps, untangling massive steel cables that had become snarled by the wind, using only their hands. It was a physical war of human endurance against the raw kinetic fury of the elements. But this is just the beginning. It only looks obvious that a straight line is the simplest path, but in reality, this crossing replaced a 3-hour journey through dangerous mountain roads. The travel time has been reduced to exactly 1 hour and 30 minutes. The structure integrated the G56 expressway into a unified network, establishing vital commercial corridors between China and Southeast Asia. One can see how the asphalt lays in an even layer across the span, facilitating the transport of goods and the arrival of tourism to a region once isolated by geography. Transition to the next level. The camera glides along the glass floor of the observation deck at the very top of the structure. Imagine standing there, looking down through the transparent surface at the river below, which appears as a thin silver thread over half a kilometer away. The bridge is composed of more than 439,000 cubic meters of reinforced concrete and 9,000 tons of high-tensile steel cables. It serves as physical evidence that no obstacle remains insurmountable when technical ambition meets high-precision engineering. What was once a lethal geographical void has been transformed into a stable platform overlooking the future. Dust slowly settles from the memory of the construction explosions, leaving behind a perfect line of industrial order. The process of shaping the world does not end at this stage. Imagine a green expanse equivalent to 1/5 of the entire Amazon rainforest disappearing every single year. This is the ecological cost required to manufacture 80 billion rolls of toilet paper consumed by humanity every 12 months. 15 million hectares of timber are harvested for this purpose. But what if the solution to preserving these forests was hidden within the materials normally discarded as waste? Everything only gets more complicated as the focus shifts from steel to the fiber industry. 500 tons of daily waste are transformed into pure hygiene within this industrial complex. Why does engineering choose to process dirty and contaminated paper into something clean enough to touch the human body? The raw material seems unusable, yet systematic purification turns this discarded mass into a medical-grade resource. The answer lies in a sequence of mechanical and chemical barriers that strip away every impurity until only cellulose remains. The journey starts with the heavy roar of diesel engines as collection trucks, true steel titans, arrive at the factory yard. These vehicles dump 500 tons of residual material every single day, creating a mountain of paper mixed with plastics, metals, food scraps, and glass. One can notice how the trucks tilt their beds slowly to discharge the chaotic heap. But this is not garbage to the industry, it is raw gold waiting for extraction. The first stage is a war against contamination, where material is pushed onto gigantic conveyor belts that move like rivers of rubber and metal. Technology here must operate faster than the human eye can track. Advanced optical sensors scan every fragment passing at high speed. It is visible how the equipment gradually identifies non-paper elements invisible to a casual observer. The process is only gaining momentum. Compressed air jets fire like invisible bullets the moment a plastic bag or a piece of nylon is detected. This mechanical gunfire expels intruders from the production line in fractions of a second. At first glance, the sorting looks entirely automated, but in reality, human precision provides the final failsafe. Workers equipped with heavy protection, including industrial masks and rubber gloves, perform a final manual triage. They remove what the machines might have missed, ensuring only paper moves forward. Separators known as vibratory screens shake the material with the force of a controlled earthquake. Physical laws here are simple and brutal as the equipment vibrates ceaselessly. Heavy, unwanted materials sink and fall through gaps, while the lighter paper floats toward the next phase. Transition to the next level occurs as the flow reaches the compaction zone. Hydraulic presses crush the cleaned material with a force of several tons to create dense, square bales. Each of these blocks weighs 800 kilograms and resembles a giant brick. One can notice the pistons extending slowly to exert maximum pressure. It gets more complex further on. A single one of these concentrated cubes contains enough raw material to produce over 10,000 new rolls of toilet paper. Matter changes state as the true transformation begins inside a structure known as a hydropulper. One can observe a forklift transporting the bales and dropping them into a tank the size of a two-story house. The vessel is flooded with water according to a strict ratio of 1 part paper to 10 parts water. But this is not just a bath. A monstrous steel rotor at the bottom of the tank spins at a staggering speed between 1,000 and 1,500 revolutions per minute. The vortex consumes the solid blocks, breaking them down into a liquid suspension. The molten-like slurry of fiber and water moves further along the production chain. 30 to 60 minutes is the exact duration the agitators maintain their relentless rotation within the pulping chamber. Why is such violent kinetic energy required at this stage of the process? The water transforms into a high-velocity vortex that strikes the recycled paper with enough force to tear it down into individual microscopic fibers. This mechanical aggression ensures that the material is not merely shredded, but completely disintegrated into its primary components. The process is only gaining momentum. Chemical agents and specialized dispersants are introduced into the swirling mixture to target and isolate printing inks and residual adhesives. One can notice how the ink particles detach from the fibers and float toward the surface or dissolve entirely into the liquid medium. The agitation continues until only pure cellulose remains suspended in the churning water. The result of this stage is a dense gray slurry, a thick suspension of fibers that lacks any structural integrity. It only looks obvious that this gray mass is ready for forming, but in reality, it must undergo rigorous filtration. Fine mesh screens receive the mixture to capture the smallest remaining contaminants, such as plastic fragments or metal staples that persisted through the initial breakdown. The equipment gradually purifies the suspension until it consists of 95% water and 5% clean pulp. But this is just the beginning. The liberated fibers begin to seek one another out, initiating the formation of natural hydrogen bonds that will serve as the physical backbone of the final product. Engineering and biology converge as the liquid pulp is pumped directly into the forming machine. The machine operates at a speed so high that the eye sees only a continuous blur as the mixture is spread across a moving fine mesh screen. Rapid dehydration is essential at this juncture. One can notice how rotating cylinders and high-powered vacuum systems apply tremendous suction to extract the moisture through the mesh. Gravity and mechanical force work in tandem to drain the liquid, leaving behind a delicate, damp web of interlaced fibers. But the sheet is still fragile and lacks its final density. The material enters the pressing zone, where massive steel rollers apply pressure to the newly formed paper with millimeter precision. It is visible how the moisture is forced out while the rollers simultaneously establish the uniform thickness of the sheet. The calibration is set to achieve a thickness of between 15 and 20 microns. This measurement is significantly finer than a single human hair or a common particle of dust. Everything only gets more complicated as the sheet moves toward the thermal treatment. The paper adheres to a massive steam-heated cylinder known as the Yankee dryer to undergo intense evaporation. Heat transfers into the fibers instantly, driving off the final remnants of moisture in a fraction of a second. Transition to the next level. What was once a liquid suspension of waste material has now been physically transformed into a continuous dry web. The material leaves the drying section, transitioning into a calm stage of the production cycle. 1 meter and 10 centimeters is the minimum diameter reached by the jumbo reels at the end of the primary production line. Why is such a massive scale necessary for a product that is ultimately so delicate? The continuous sheet moves through the machinery at high speeds to maintain tension, as any slack would result in structural defects. This ensures that the material